In this tutorial, we'll take a look at the binomial theorem. And on the first real page here, we're expanding out the binomial, the sort of a generic binomial a plus b. So this is a plus b to the 0, a plus b to the first, a plus b to the second, etc. Of course, anything to the power of 0 is 1, so that's why we start with a 1 here. A plus b to the first would just be a plus b. If we expand out a plus b squared, we get a squared plus 2ab plus b squared. And we're going to take a look at some of these expansions on the next page. What's down the bottom here, and this is actually, if you've seen it before, this is Pascal's Triangle. It's all the coefficients of the a and b here, all the terms. And so we start with a 1 up top here, and this is 1a plus 1b. That's why there's a 1 here and a 1 here. 1a squared, that's why that's a 1, plus 2ab, there's a 2 there, plus 1b squared, that's a 1 there, etc. And so these are actually the coefficients of all the terms. So for example, across the bottom here, it goes 1, 5, 10, 10, 5, 1, and that's these numbers across the bottom there. And they're very useful, and we'll get into where they come from. So, as I said in the previous page, we'll take a look at where some of those expansions come from. So, for example, a plus b squared is a plus b times an a plus b. There's two of them. And so we go a times a is a times a, or a squared. A times this b is this ab. And then b times this a is another ab, or ba. And those are actually like terms. ab and ab add to 2ab. And then we have b times b in the end. That's 2b's multiplied, or b squared. Now, notice there's two of these AB terms, because when you're multiplying two binomials together, there's two ways to get an A and a B multiplied. You can multiply this one by this one, or this B by this A. So that's why that's a 2AB. There's only one B squared term, because there's only one way to get two B's multiplied. This B times this B, and that's it. And the same with the A squared. If we cube a plus b, that means 3ab's multiplied. So for example, and we don't normally multiply, or most people don't, 3 together at the same time. But you can do that if you're very careful about what you're multiplying. So for example, this first term here, the a times a, which is where the a cubed comes from, is actually found by multiplying this a by this a by this a. There's only one way to get 3 a's multiplied together. That's why there's a 1a cubed there. Well, there's several ways to get two a's and a b. You could go this a times this a times this b, or you could go this a times this b times this a, so maybe that's that term right there. And another way to get a b and two a's is you could multiply this b by this a and this a. And all these terms are always multiplying a single term in one binomial by a single term in an x by a single term in another binomial. And so this is, we would normally call this an a squared b. It doesn't matter what order it's in, a squared b, a squared b. There's three of them. And the reason there's a 3 there is because there's 3 ways to get 2 a's and a b. And we could go similarly through the whole thing, the rest of it. There's also 3 ways to get 1 a and 2 b's. And those are the 3 there, so that's why it's a 3ab squared. And there's only one way to get a b cubed, which is this b times this b times this b, which gives you the b cubed. One more of these, and I'll get into explaining a little bit about what the binomial theorem is in this one. If we, excuse me, expand out a plus b to the fourth, it means 4 of these multiplied. So there's only one a to the fourth term, because there's only one way to get 4 a's multiplied. It's this a times this a times this a times this a, etc. So that's the a to the fourth. Now, there's 4 ways to get 3 a's and a b, which would be an a cubed b term. You could go, let's see if I can duplicate this, a times a times a times the b. So let's say that's that term. You could go a times a times a b times another a, so that's that term. In fact, actually go in order. I guess it's not too hard to get this straight. The AB, AA comes from a times b times an a and an a. That's that term. And then the last one, we start with a b and then go a, and that's that one there. So there's 4 ways actually to select a term from each one and multiply them and get 3 a's multiplied and a b. So that's why there's a 4a cubed b, because of course a times a times a is a cubed. Now, and we could keep on going through. There's actually 6 ways to get 2 a's and a b multiplied. Or sorry, 2 a's and 2 b's. And then 4 ways to get 1 a and 3 b's, just like there was 4 ways to get a cubed b. And there's only 1 way to get a b to the 4th. Now, if you've seen combinations at all, the combinations can help to explain, so you don't have to do this every single time, where those coefficients come from. And we'll get into the binomial theorem shortly after this. What we're doing here actually is we're selecting 4 letters in each one of these. From there's now altogether there's 4 A's and 4 B's altogether, but you're only selecting 4 letters at a time. And in this first one, it's all A's, a to the 4th. Notice there's no B in that at all. So there's actually one way to select from 4. You've got 4 A's, but you're not selecting any B's. So if you think of the combination, then there's four letters, and you're selecting no B's. In the second one, and you could reverse and do the A's if you wanted to, we're selecting 3 A's and a B. So we're selecting 4 letters, and only one of them is a B. One of them is a B, so 3 of them are A's. So that's why we could write that 4 as 4 choose 1. We're selecting 4 letters, and only one of them is a B. The second one, there's 2 B's. So we're selecting 4 letters, and there's 2 B's. So we could write that combination as 4 choose 2. And then the third one, we're selecting 4 letters, and 3 of them are B's. So there's 4 choose 3 ways to do that. And so that's why that combination, that coefficient is 4. And then the last one, we're selecting 4 letters, and all of them are going to be B's. So 4 choose 4 is 1. That's why it's just 1 B to the 4th in the end there. So you can actually use combinations to get the coefficients in any binomial expansion. And that's just an example of why the binomial theorem works. So the binomial theorem says that if you have, let's say the binomial, we'll call it a plus b raised to the power of n, then this is how you can write out the expansion and using combinations for the coefficients. So the exponent is n here, so every combination will start with an n. It's n choose something. And in the first one, we start out with a raised to the power of n, b raised to the power of 0. Just like in the previous page, this first term, now it's the expansion of 4 here, so a starts at the power of 4 and goes to 3, and then 2, and then 1, and then actually a to the 0 here actually. B starts out with an exponent of 0, so there's no b here. B to 0 is 1. But then we go b the first, b the second, b the third, b the 4th. Notice that the 2 exponents, like 4 and 0, 3 and 1, 2 and 2, 1 and 3, 0 and 4, always add to the power that you raise the binomial to. So the first coefficient is always going to be n choose 0. It starts counting at 0. And then a raised to the power of n, b raised to the power of 0. So the first term from the binomial raised to the power of n, the second one raised to the power of 0. The next coefficient would be n choose 1, and then the next one's n choose 2, and the next one would be n choose 3, etc. Out down to the last one would be n choose n. That gives you the coefficient for the last term. Notice that a starts at the power of n, and then n minus 1 and n minus 2. The next one would be n minus 3. B starts counting at 0 and up to 1, up to 2. The next one would be 3, etc. So by the time you get to the very end here, a is actually down to having an exponent of 0, and b would be up to n. And once again, all the way through here, the 2 exponents always add up to n. 1 and n minus 1 add to n. 2 and n minus 2 add to n, etc. So, and this is true for any natural number n and real numbers a and b, or terms a and b. And so we're going to take a look at a few examples of using the binomial theorem to expand out binomials. And actually I'm going to use the binomial theorem at some, and some I'm going to use Pascal's triangle, because some people like that method a little bit better. So y plus 2 to the 5th. Oh, and Actually, what I did up top here was I just rewrote this with b to the power 0 is 1, so I don't really need to write that in, and a to the power 0 is 1, which I don't really need to write the a to the power 0 in, and so that's the only difference here. So a lot of times you'll see it written like this, so there's kind of looks like there's no b term here, but there actually is a b to the 0, etc. So, expanding out y plus 2 to the fifth. The very first term, now n is 5 here, so the first combination would be 5, choose 0, and we would start the y at a power of 5, just like we're starting a here raised to the power of n, so it would be y to the fifth. The next coefficient would be 5, choose 1. And then y goes down 1, the exponent goes down 1. And now there's actually a 2 to the power 0 here, but we don't normally write that. So this would be 2 to the first for the next one. And then the next coefficient would be 5, choose 2. Y's exponent decreases by 1, and the 2's exponent increases from 1 to 2. Just like up here, b to the power first, b to the power second, etc. Next term would be 5, choose 3. 5, choose 2, and then we go 5, choose 3. The y's exponent decreases from 3 to 2. The 2's exponent increases from 2 up to 3. And then the next term would be 5, choose 4. Be y to the first. Again, y's exponent goes down by 1. The second part of the binomial, the 2 in this case, exponent increases from 3 to 4. And then the last coefficient would be, or combination, same thing, would be 5, choose 5. We don't bother to write a y in here because it would actually be, this is y to the first, so there would be a y to the 0 here, which is 1, so you don't bother to write that. And then 2 raised to the power of 4, and the next one's 2 raised to the power of 5. And then the next goal is actually just to simplify each individual term. This is going to be a term, this is going to be a term, this is going to be a term, down to the last one. So the first one, 5 choose 0 is 1, y to the first then. The second one, 5 choose 1 is 5. We have a y to the fourth, and then times a 2. There's nothing really to evaluate there. 5 choose 2 is 10, y cubed, and then 2 squared is 4. 5 choose 3 is also 10, and then we have a y squared, and 2 cubed is 8. 5 choose 4 is 5 times this y, and 2 to the fourth is 16. And then the last term, 5 choose 5 is 1. 2 to the fifth is 32. So we have a few terms to simplify. The first and last one are kind of done. 5y to the fourth times 2. 5 times 2 is 10, so that's 10y to the fourth. 4 times 10 would be 40, so we have a 40y cubed here. 10 times 8 is 80, so this would be 80y squared from this term here. 5 times 16 is also 80, so we have an 80y here, and then 1 times 32 is just 32. So that's, if you were to multiply 5 different y plus 2's, or I shouldn't say different, they're all the same, together, and expand that whole thing out, then this is the terms that you would get. So the binomial theorem is a bit of a shortcut. It's an organized way to do that, so you don't miss any terms. Okay, now this is another example. I kind of called that example 1, and I'll call this example 1 again, because I'm going to show how to do this using Pascal's triangle instead of the combinations. So in Pascal's triangle, the row that corresponds to 5, and you can go back to the, I guess it's the second page of the note, is 1, 5, 10, 10, 5, 1, if you want to refer back. And so this is what I wrote in the last page. So in place of these, I'm putting the 1 here, the 5 here, 10, see this is going to be 10. The next one, this coefficient would be 10. And this 5 will be this 5 choose 4 here, and then 1 at the very end, so 1 in place of this. So it's kind of like, instead of writing this, we can write the same thing but with those numbers from Pascal's triangle. So if I'm using Pascal's triangle, I would not normally write this out. I would write this instead. So it's not like I'm doing both of them. And so, same idea as before, we simplify the powers. 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32. And then simplify all terms. That's going to be 10y to the fourth, that's going to be 40y cubed, 80y squared, and 80y, and then 32 in the end. So, of course, you get the same thing. But I'm just trying to show you how, using Pascal's triangle, you can write out what the coefficients would be instead of using the combinations. So just a slightly different way to do it. Okay, another example, 4x minus 3 raised to the power 6 is what we're expanding. So, of course, you could expand 6 of these 4x minus 3's together. That would be a lot of algebra. So using the binomial theorem, the first, since it's the power 6, the first coefficient would be 6, choose 0, and then we would raise the whole 4x to the power of 6. Not just the x. Notice that the whole term 4x is raised to the power of 6. There's brackets around the 4 and the x. Next coefficient would be 6, choose 1. Then this becomes the power of 5, and then we have a negative 3 to the first. There's actually a negative 3 to the 0 here, but we don't normally write that because it's the power of 0. Power of 0 equals 1. And then we go to 6, choose 2. The exponent of the 4x reduces to 1. The exponent of negative 3 increases to 2. 6, choose 3 is the next one. And again, the exponent in the 4x decreases by 1. The second part of the binomial increases by 1. It was 2 there. It's 3 here. 6, choose 4. 4x squared. And then negative 3 raised to the power of 4 now. And then 6, choose 5 would be the next coefficient. 4x to the first now. See, was squared there. Now it's power 1. This was the power of 4. Now it's power 5. And then the last term is 6, choose 6. See, whenever these two numbers in the combination are the same, that's the last term. Like, you can't evaluate 6, choose 7, for example. It doesn't exist. And then negative 3 raised to the power of 6. Notice it increased by 1 again. So we need to simplify all the combinations and then the powers as well. 6, choose 0 is 1. 4 raised to the power of 6 is 4,096. And of course, x raised to the power of 6 is x to the 6th. 6, choose 1 is 6. 4 to the 5th is 1,024, and that would be x to the 5th times this negative 3. 6, choose 2 is 15. 4 to the 4th is 256. Don't forget to evaluate the 4 raised to the power of 4. It's a really common mistake to write, and now this is x to the 4th, to write just 4x to the 4th and forget to do the 4 raised to the power of 4 as well. Negative 3, of course, squared is 9. From this term, 6, choose 3 is 20. 4 cubed is 64, x to the 3rd, and negative 3 times negative 3 times negative 3, or negative 3 cubed is negative 27. 6, choose 4 is 15. 4 squared is 16, x squared, and negative 3 to the 4th is 81. 6, choose 5 is 6 times 4x times negative 3 to the 5th is negative 243. And this last term, that combination is 1. We have negative 3 raised to the power of 6 is 729. Now, notice that these numbers are actually, well, there's actually a 1 here. 6, 15, 20, 15, 6, and there's actually a 1 here. Those are actually the numbers from Pascal's Triangle, if you want to use Pascal's Triangle. So we have 4,096 x to the 6. 6 times 1024 times negative 3 is negative 18,432 x to the 5th. 15 times 256 times 9 is 34,560, and then x to the 4th. 20 times 24 times negative 27 is this coefficient, x cubed. 15 times 16 times 81 is 19,440, and then x squared. 6 times 4 times negative 243 is negative 5,832, and then it would be x, there's just an x there, and then plus the 729 in the end. So that's what that expansion would be if we expand out 6 of these 4x minus 3's multiplied. Now, last example here, sometimes you might have a long expansion, but you only want one specific term. And so this is actually from the binomial theorem. The general term of a plus b to the n is, and we call it term plus 1, and that's because in the combination r starts counting at 0, not at 1. That's why it's term r plus 1. And this is actually just the general term from the binomial theorem. It's n choose r, a to the n minus r, b to the r. So if you want to look back at that formula, that's the general term of the summation. And example 3, we're asked to find the 9th term in this expansion. So now, if it's power of 14, there's actually 15 terms. Because remember, r starts counting at 0, so if in this case it would go from 0 up to 14, that's 15 terms. But we only want the 9th one. So what you do to find that 9th term using this general term is tailor this general term to this specific expansion. And so there's the general term formula. And in it, the n would be 14, so that's why we put 14 here. 14 choose r. The a refers to the first term from the binomial, which in this case would be x. So we would have x raised to the power of, and n is 14, so it's 14 minus r. The second term in the binomial is the 3y, so that goes in place of b. Remember, it's a plus b, so that's why there's a 3y raised to the power of r. So this is the general term formula for that specific expansion. Now if we want the ninth term, we want term 9, we have to figure out what number do we put in place of r to get term 9. If you put 9 in here, 9 plus 1 is 10, you'd actually get the 10th term. You want this subscript to be equal to 9, so you'd need to put 8 in place of r, because 8 plus 1 is 9, and it would be term 9. So we have to use r equals 8. So you put 8 in place of r, so this is going to be term 9. So we're putting 8 in place of r, so the combination is 14 choose 8. And then be x to the power of 14 minus 8 here. And then 3y is raised to the power of 8, again, because we're putting 8 in place of r. So 14 choose 8 is 3003. 14 minus 8 is 6. 3 raised to the power of 8 is 6561. And of course y to the power of 8. So we multiply these together. 3003 times 6561 is 19,702,683, and then x to the 6, y to the 8th. So that's what the ninth term would be. Now there could be times where you're asked to find a specific term that has a specific power of x or y or whatever the variables are. So what you would do is go back to your term. So let's say you were looking for the term, let's say, that had an x to the power of 10. Let's say it was so let's say you're trying to find the term that has an x to the power of 10. Okay, so where's the term that has an x to the 10th? This is the only place in the general term formula that a power of x can come from. So what you would do is take that exponent, the 14 minus r, and set that equal to the 10, because you're looking for terms with x to the 10th. And so r would have to equal 4 here. And so the way you'd get the term is in the term form, you put 4 in place of r. So we put 4 here. So it would actually be term 5. So we're going to put 4 here in place of r, and 4 here. And so it would be the combination 14 choose 4, x to the, now you could write 14 minus 4, which of course is 10, and then times 3y raised to the power of 4. And you could evaluate the combination. This is going to give you the x to the 10th here. And then, of course, 3 to the 4th is 81, so 81y to the 4th. And I don't have my calculator on me, so I'm not going to do the 14 to the 4th right now. But whatever that number is for that big combination, times 81, that's the coefficient, and it'd be x to the 10th, y to the 4th. So that's how you can find a specific term that has a certain power of x, or whatever the variable might be. And that's the end of the tutorial.